Hi everyone, thank you for coming this afternoon. Today's speaker is Vesna Lukic, who did her master's in physics in Melbourne and then worked as a bioinformatician analyzing genetic data before starting her PhD in astrophysics in Hamburg. And she's going to be talking today about the deep learning applied to radio astronomy, which is the topic of her PhD. So please welcome Vesna.
Thanks very much for the introduction.
Oh, sorry, and that's the microphone.
Okay.
Okay, there you go. Sorry.
Or do I click it somewhere?
Yeah.
Yeah, I'd like to thank Peter for the invitation to be able to present my work here. I feel very privileged to be able to talk about what I did during my PhD. So this was actually work that was submitted last month, and my defense should be on the, later in the month on the 26th of November. So if we looked up at the night sky and our vision enabled us to see radio waves, this is an image of something that we might see. The individual white spots are not actually stars. They are in fact radio galaxies, and the larger white blobs are supernova remnants. And radio galaxies, which form the focus of what I did in my PhD, they fall into a certain category of active galactic nuclei called radio-loud AGNs, radio-loud active galactic nuclei. And they fall into two morphologies in the broader sense. The first being compact or point-like sources, and the second being extended sources. Now, they can be compact due to being unresolved by the telescope, and as a result, they tend to have a point-like structure and generally have simple morphologies. However, we should note that there are some extended sources that can be compact as well. And so there's some debate about whether they should form a radio galaxy class in their own right, or whether they're different type of radio galaxy in the early stages of evolution. But yeah, they can also be resolved and compact as well. And then what's more commonly seen is extended sources that have a broader range of morphologies. So these types of sources tend to be resolved by the telescope, and they have patterns of emission that can cover quite a broad range of morphologies. And this is what we are interested in classifying between these two different types of sources. And with extended sources mainly fall into two different types of categories. There's either the Phaneroff-Riley type 1 class or the Phaneroff-Riley type 2 class. So radio galaxies typically have three components. They have a core, jets, and lobes. And it was Phaneroff and Riley that first recognized that there is a correlation between what parts of the radio galaxy are most luminous and the morphology. So FR1 types tend to have the brightest part of the emission towards the core of the radio galaxy, and FR2s tend to have the brightest part of the emission towards the lobes. And then I've also put in an image of what a compact source looks like as well, what a resolved compact source looks like. So you can see around the main point, there's some extended emission. And then there are also rarer types of radio galaxy sources, such as bent-tailed classes, which can be narrow-angle-tailed or wide-angle-tailed, depending on the angle that the tails make with each other. And then another rarer class was called the hybrid type galaxy, which tends to display a mixture of the FR1 and FR2 morphologies. And to add more complexity into the mix, the more technology is being developed, the radio telescopes are becoming more sensitive and able to detect emission at higher resolution. And so this gives rise to variabilities of what morphologies can look like within classes as well. So these are some examples of what FR1 types can look like. is just a few examples. And the same for FR2s. So they can take, the emission can take a whole range of morphologies even within the classes. So that makes things more complicated. And the reason why we want to classify the radio galaxy morphology in the first place is that it reveals some important characteristics about the galaxy. So it tells us something about the surrounding environment. So at low redshifts, FR1s tend to be found in galaxy clusters or groups, and FR2s tend to be hosted by field galaxies. And at higher redshifts, both FR1s and FR2s tend to be found in dense environments. And almost all the information that we know about jets has some relationship in terms of how luminous the jet is, as well as its morphology. And so the more surveys are performed, the more the high quality sources that are detected that have, because the telescopes work at higher resolution and higher sensitivities. And so here is a graph showing from the beginnings of radio astronomy how many sources were detected on a log scale compared to the present day for different types of radio telescopes or arrays. So you can see there's a real exponential increase in the number of radio sources that have been detected by the different surveys. And so you can imagine that manual analyses by professional astronomers will become increasingly impossible with such large data volumes. And so there are two ways, there can be two ways to go about this. One is to use citizen scientists or automated machine learning methods. So when using citizen scientists, these are essentially non-professional scientists that can be taught based on the fact that images form certain patterns. You can teach citizen scientists to recognize certain patterns and therefore make classifications. And one of the first examples of this is in the Capsule Galaxy Zoo competition, which I'll talk about more in the next slide. And then you can also feed these inputs from the citizen scientists to train a machine learning algorithm to try to replicate the way that they have classified galaxies or other scientific data. But you can also get, based on the fact that you can you can recognize certain patterns of morphologies for certain classes, you can also train a machine learning network from scratch to try to recognize them. So in regards to the Capsule Galaxy Zoo competition, so this is where citizen scientists were asked to describe the morphologies of optical galaxies. So they were asked a certain number of questions. So for example, is the galaxy in the center of the image smooth and rounded with no sign of a disk? And then they have to click on which image best represents the one in question, or other responses were yes and no to different types of questions. And so the overall aim of the competition was to use the probabilities that a whole bunch of citizen scientists have given in response to these questions. So for this question one, they might have given 85 might have said it's smooth, 5% have said it's artifact, and then 15% have said there's features or some disk. And then so the overall aim was to get the competitors for the challenge to try to predict how the citizen scientists have classified them as a whole. And so it wasn't a classification problem, it was a regression problem. And the winning solution actually used convolutional neural networks. And this is the first time I've heard of such an approach. And given that it showed a promising performance in classifying optical galaxy morphologies, we thought it might perform similarly for classifying radio galaxy morphologies. And so the way that convolutional networks work is that they are built off how neural networks work. So you have an input layer and an output layer, where in the input you feed in the data such as, which in our case is images. And then you can also have, in the supervised learning context, labels that go with this set of with images. And then you also initialize your network with a set of weights and biases from a random distribution, and then you propagate the information through the network. And in the final layer, you calculate the error, which is based on some function of the difference between the label and the prediction that the network gives. And so then this error is propagated back through the network, and the weights and biases are adjusted in order to minimize the error. And when you're training a neural network, you essentially want to keep decreasing this cost function or loss, and you hope that by the end you reach a global minimum rather than get stuck in a local one. And so you've, I guess, optimally trained the neural network once you find the global minimum. And you can imagine that the more complex the data and the more classes you have, you would need more layers and more nodes in each layer to capture the complexity in a data set. So you would need to add more and more layers. However, the problem with this is that you can run into something called the vanishing gradient problem, which is when your gradient continues to decrease and then can eventually go to zero, in which case your networks stop to learn. And so this problem is actually remedied through the use of convolutional neural networks, which instead of having all the adjacent layers with the nodes interconnected between each other, they instead use a set of user-defined filters where the user specifies how many to use and what size they are, and these filters scan across the image and detect features. And it doesn't matter where the feature is in the image, whether it's on this end or this end. The way that they are built is that they ensure translational invariance, and because they detect the same features are detected at different parts of the image, that they produce similar activations. This reduces. The overall effect is through using filters, you reduce the number of parameters in your network. And you further reduce the number of parameters through the use of pooling. And the way that pooling works is that, for example, in max pooling, you look at a certain local part of the image and you put forward the maximum value from that area. And although this reduces the parameters, this can also inevitably result in some information loss. So this is something that we look into later. But the overall result of stacking convolutional and pooling layers is that you get a hierarchical extraction of features that have fewer parameters than if you were building a deep neural network just with all the nodes interconnected. And so the first project that we have applied these convolutional neural networks to are in the Radio Galaxy Zoo dataset. So we have image data of more than 200,000 galaxies. However, despite this high number, we didn't have any labels to go with them. And so if we wanted to pose our problem as a supervised learning problem, we needed to think how to generate labels, and this is what route we chose to take. And the data is single channel, so it's black and white of typically 132 by 132 pixels. And we have assumed that each image is of an individual radio galaxy. And so we then assume that each of these individual galaxies has a certain number of components in the image. And based on this assumption, we can use the Python blob detector and source finder, or PyDSF, to help organize the data in how many components there are. And it was able to successfully process more than 175,000 images. And so the first problem that we posed was actually the two-class problem of trying to develop a deep neural network to distinguish between the two morphological extremes of point sources and multiple component extended sources. The reason why we chose such morphological extremes was because we figured it would be easy to see what changes to the network would improve the performance of the network as opposed to make the performance worse. We thought it would just be obvious to see what changes make things better or worse when we make them by using these morphological extremes. And so in this way, we have experimented with changing the number of layers in the network and seeing how much of a benefit you get with using augmented images along with your original ones, as well as how much the performance can be affected by using only a subset of images. And so we have also experimented with changing the number of pooling layers and using sigma clipping or not. And so the neural network library that we built was actually in Lasagna. So this library was built by the winner of the Galaxy Zoo competition. So he released this package in order to help people to build convolutional networks for similar problems. So this is the library that we originally used. And so we have tuned our neural network manually to find the optimal setup. And this is common practice. Most of the time it's done through trial and error. We pick some parameters, we see how it works, and we try other ones and hopefully explore enough space to get good performance. So we found a small batch size of 8 tended to do the best compared to larger batch sizes. We set the learning rate to 0.001 at the start and reduced it several times during training. We used the categorical cross-entropy cost function and trained for a rather long number of epochs, but again, we had hundreds of thousands of images to train with. And we used the mini-batch stochastic gradient descent as our descent method. And so, unsurprisingly, we found that the best results were obtained when we used the augmented images in addition to the original ones. And we found that the 3 convolutional and 2 dense layer architecture performed the best, achieving a classification accuracy greater than 97%. And you can see in this training and validation loss curve that when we only use 2 convolutional and 2 dense layers, that we experience some level of overfitting, which means that you can afford to make your network a bit more complex so that the training validation losses can be more even. And so this is exactly what happens when we add 1 extra layer. It tends to result in a smaller loss, and then the training validation losses are around the same level. And so given that we have optimized our network for the 2-class problem, we wanted to see how we would fare in the 4-class problem of distinguishing between compact sources and 3 classes of extended sources. So in our extended sources, we have a single component in the second row, a 2-component extended in the third row, and greater than or equal to 3 extended component sources in the final row. And so when we applied the same architecture to this setup, we found that we still got pretty good results. It didn't get as good as it didn't perform as well as it did for the 2-class problem. It didn't get above 97%, but it got 93.5. But it did a bit worse because I guess there's more classes, so there's more risk of overlap between the classes. However, it still does pretty well overall, and there's not much overfitting observed in the training validation loss curves. And then we also wanted to perform a cross-check with the data release 1 of the Radio Galaxy Zoo. So the data release 1 essentially consisted of citizen scientists trying to tell whether or not the components of a radio source belong to one particular source, or whether they belong to a different one. And so it involved them counting the number of peaks and the number of components in the radio sources. And then in order to apply our trained neural network to this problem, we had to see what images we had in common with our 4-class problem with that in the data release 1 data set. And we found that there were just under 7,000 that were in common. And then we felt it was necessary to collapse the number of peaks and the number of components information from the citizen scientists in order to use the same classifications that we had. And we also had to collapse the component and single component, the single extended, the compact and the single component extended class, because there was no way to tell between the two based on the data we were given. And so if a radio source had two components and 2 peaks, it belonged in the 2-component extended class, and similar reasoning for the final class. And so upon application of our trained neural network onto the data release 1 dataset, we find again we get the best results when we use our augmented data as well as the original ones. And we found that the classification accuracies do look pretty good, but upon closer inspection, we found that this was mainly influenced by the fact that most of the images belonged into the compact and single component extended class. And so this is what drove the high accuracies, because those were the simplest morphology and were easiest to identify. And you can see the performance decreases the more components that are added. And it's especially poor with the multiple component extended class, where the precision and recall is really rather dismal. And so the situation can be improved when you generate augmented images and you use them as well. And so we see that the poorest performing class tends to improve the most. However, it's still the poorest overall. And so, yeah, you can get some improvement using augmented images, but it's still not ideal. And the reason why we think that our networks might not have been working very well with this data set is that perhaps it was the use of the pooling layers that ends up in some information loss. So essentially, the more components that you add to a radio to an image, the more information that you risk losing, essentially, because the components can be oriented differently with respect to each other. The more that you have, there's more degrees of freedom. And so we think that the pooling operation might be responsible for causing this information to be lost and therefore affect the performances of the neural network. And so although in convolutional networks, the translational invariance is preserved through the parameters being shared, there's a real lack of rotational invariance because of the use of pooling. And so how the features relate to each other on a global scale tends to be lost the more pooling layers that you use. So we think this is what was going wrong with our first project in the multiple component extended. The higher the number of components, the worse the performance was. And so you can imagine if you look at what this what's most likely an FR2 type galaxy, then if you take the top part of the image and you rotate it and you put it back, you might fool the neural network into thinking that this is still an FR2 when actually now the morphology is nonsensical. It looks like it might be two independent sources or some hybrid type source. And so this is worth taking into account. So this is where capsule networks are being invented. So they've been specifically designed to help preserve the hierarchical relationships in images. So not just the local information, but how the features relate to each other on a global scale. They aim to preserve this. And the way that they work is that a capsule consists of a group of neurons that essentially try to get the underlying morphology that underpins all the different types of images within a certain class. It tries to get the representative morphology of what images in a particular class look like. And so then you can imagine applying a range of transformations to this representative image and see all the different changes that you can make to it in order for the image to still be in the same class. And so in our second work, this is how we have applied specifically this capsule network architecture and compared the performance against convolutional neural networks. And so, and the sources that we used for this project are from the LOFAR 2-meter sky survey. And so one bit of information that we had in this project that we didn't have in our Radio Galaxy Zoo project was cross-identification information using other wavelengths. So whereas in the first project we had to make the assumption that each image was of an individual radio galaxy and all the components belonged to that one image, we couldn't. That was a fair assumption in most cases, but it couldn't be applied. It might not have applied to every single image that we used. And that might have also contributed to the poorer performance of our convolutional networks. But in this project, we do have cross-identification information of radio sources with the corresponding optical source. And the way that this was done was that for sources that were smaller than 15 arcseconds, they were cross-correlated using an automated method called the maximum likelihood technique. And for sources that are larger than 15 arcseconds, they were actually inspected by expert astronomers. And these expert astronomers were composed what's called the LOFAR galaxy zoo. So it consisted of a panel of professional astronomers essentially clicking on the images and associating components to particular sources. And so, in contrast with our first project, we had drastically reduced number of training images, of original images compared to in our first project where we had 175,000. Now we have just under 3,000. But they were with confident classifications into the classes of unresolved or compact and FR1 and FR2 morphologies. And we were given the original FITS file cutouts with the original radio emission in them, and as well as 4RMS sigma clipped numpy arrays where background noise below 4RMS was removed, as well as potentially unassociated sources. And the way that the labels were generated was using an automated technique using the 4RMS images. And the way this was done was that the points, the LOFAR galaxy zoo identified points of maximum emission and where the core was and where the extent of the emission was. And so there are some rules that FR1s and FR2 follows in relation to the ratios of distances between these different features. And so that is how they were classified using an automated algorithm. And they were additionally cross-checked by a third party to make sure that the algorithm was classifying them correctly. And we also applied the usual image augmentation techniques such as translation, rotation, and flipping to generate augmented data. And so the table here shows the breakdown of how many original images there are in each class and how many augmented images we also made. And we found that we got the best performance when we kept the ratio of FR1s to FR2s the same as in the original data set. And so in the end, we had just under 16,000 images for training and testing. And then here is a visual representation of what the data looks like. So on the left is shown the original radio emission in form of FITS files, and the bottom is showing the corresponding images, but using the 4RMS signal clipped numpy arrays. And you can see the unassociated components and noise is removed. So for example, in this image, this unassociated source is not present there. And so the same thing for this one. And so yeah, these images are cleaned images of the original data into the 3 different classes. So they're just showing representative images of what our data looks like. And then there are 2 convolutional neural network architectures that we've explored in classifying this data set, one having 4 layers and one having 8 layers. And then we changed to using the Keras library as opposed to the Lasagna library in the first project because we actually found Keras was more user-friendly. And we set the learning rate to 0.001 using the cross-entropy cross function. We trained for 50 epochs using a batch size of 100 and using the atom optimizer. Again, these were manually tuned because they seem to perform pretty well for the data set at hand. And then for the capsule network, this is the architecture that we used. So there was actually an original capsule network code that we downloaded from GitHub that was geared towards the MNIST handwritten digit data set. However, we made our own default version from this code to make it suited more to our data. And so the architecture shown here is the default one that we made. So and we also experimented with increasing the size of the filters as well as the stride because our images were bigger compared to the MNIST dataset and they displayed more complex patterns of emission compared to the dataset that it was originally built for. And then we also increased the complexity of the decoder to try to reconstruct the images as accurately as possible. and change the weight of the loss function and increase the weight of the loss function. And you can see here, this is an image of what is most likely an FR1 type galaxy with a bit of unassociated emission to the right. And you can see that the features detected by the primary capsule layer indicate that it might be preserving this bit of unassociated emission in the original image. So this might signal some problems that the capsule network might be encountering. And so the data sets that we've tested are the original FITS files as well as the FLORMS NumPy arrays. We've used also augmented images for both these data sets, and we used 80% for training and 20% for validation testing. And because every time you train a neural network and you subsequently test it, the performance can vary slightly. We did 5 training runs and test runs and calculated the 95% confidence interval to get a bound on how much the performance can vary. And so the results that we got was that, again, the best results were obtained when we used augmented data with original data. We found that the convolutional network architectures tended to perform around the same. The one with the 8 layers didn't perform much better compared to the one with 4 layers, but it still did a bit better, but not significantly. And then we found that our default capsule network architecture that we found does the best compared to the variations of capsule networks that we tried. But still, it didn't matter what we tried to do to the capsule network, we could not get it to perform better than our convolutional networks. So it just tended to fall below 90% accuracy. And then when we employed transfer learning, we didn't get something much better than what our neural networks, than our convolutional neural networks were giving. And we think that maybe this is because we used the trained data set that was trained on, the trained network that was trained on ImageNet data. And so these are, although this has 1,000 classes and many thousands of images within each class, it's the nature of the images that are completely different to our radio galaxy data. So the data set is essentially like everyday pictures or scenes. And so we think that maybe if we used a network that was trained on radio galaxy data, then maybe we might see an improvement, a significant improvement compared to how the convolutional neural networks were classifying our data. And then we also found that we got the best results using the 4RMS sigma clipped NumPy arrays. And so this means that neither the convolutional networks or capsule networks can be made completely robust to the removal of noise and unassociated emission. So they always benefit from the explicit removal of this of these intruding features. So yeah, you can't train them to be completely robust to them based on using the original data. And then, the capsule networks always seem to perform a bit worse compared to the convolutional networks. And then to see the features that are detected by the 8-layer convolutional network, so we see for the same input image that I showed for the capsule network, this FR1 with this unassociated emission to the right, you can see it's still present after the second convolutional layer, but by the 4th one, it tends to be filtered out. And then to see maybe why the capsule network is not performing as well as it maybe it should is we can take some original images. So the original images are shown in the top, in the first row and the third row, and the corresponding reconstructions from the decoder of the capsule network are shown in the second and fourth row. And we can see that the network is really not reconstructing the original images accurately at all. It's especially not capturing the fact that FR2s generally have 2 components to them. It's not capturing the lobes, the extended emission, the pattern of the emission. And the way that it's determining class membership is essentially according to the fuzziness of the reconstructed spheres in the center. So, but even though these reconstructions are really quite inaccurate, it's still enough to ensure just under 90% accuracy. So the way that it's determining the class membership is that the unresolved sources tend to be the most point-like reconstructions, the FR2s tend to be the most diffuse, and the FR1s are somewhere in between. And so what we think is happening is that maybe the capsule network seems to be having trouble knowing what features are noise and what features are signal. It has trouble distinguishing between unassociated features, and so it might be preserving all this information without knowing what to remove. And it seems ironically that what we thought was a detriment in convolutional networks through the pooling operation, it might actually be advantageous to us in the particular data set that we have, because it seems to be removing unassociated emission as well as noise signals. So at least for the data set that we had at hand, it seems like the pooling actually might be making the network perform better than the capsule network. And it also might be giving more degrees of freedom for the morphology within the classes as well, because it gives more flexibility as it essentially it results in some information loss, but maybe that's what is required to make the flexibility in these networks for the data set at hand. But that's not to say that if we had many more, perhaps thousands of images of FR1s and FR2s, because we only had just under 3,000 images, and although we generated augmented ones, there weren't enough original representations of each class that the capsule network might actually benefit from and perform better than the convolutional networks in. So maybe this is what might happen if we had more images, but at least for the data set that we had, for the type of images that we had, we found that the traditional convolutional networks work better. And then in our third and final project, we have changed tact a bit. So whereas our first two projects focused on the classifying radio galaxies according to the number of components in the first project, and our second project involved classifying into unresolved FR1s and FR2s and comparing the performance of different types of deep learning setups. Our third project actually uses we aim to see whether you can use a deep learning framework to perform source finding in radio astronomical data. And so the data set that we have applied this method to is the simulated data from the Square Kilometre Array, or SKA. So the SKA aims to be the world's largest radio telescope, and it aims to achieve greater than 1 square kilometre of collecting area. Will hopefully detect up to 500 million sources by the time it finishes running. And in order to prepare everyone for the onslaught of data that will be obtained by the telescope, they presented people with this Science Data Challenge 1, where they encourage people to try existing source finders or develop their own source finder to detect sources in the data that they've simulated across different exposure times and different frequencies. And so the challenge wasn't just to find sources, but also to characterize and classify them. But for this project, we are just focusing on the source finding aspect. And so the simulated data looks like this. So there are 3 frequencies and 3 different exposure times. There are different patches of sky there between the different frequencies, but the same patch of sky is used between the different exposure times for each frequency. And so you can see that as the frequencies increase, the data tends to become more noisy, and as the exposure time is increased, it becomes less noisy. And we actually just focus our attention on the first 2 frequencies, because in the last one, neither our method nor another method could identify any sources accurately in that data set because of the high level of noise. And so before we embark on the problem of source finding, we first have to get a consensus for what is defined as a source. So it's generally defined as some collection of pixels that have some level that is above a certain threshold level, and this threshold is is calculated by estimating the background noise level. And the issue with source finding in radio astronomy particularly is that in contrast to some other wavelengths, it also displays signatures of correlated noise. And so the problem with this correlated noise is that it might look like it's an actual source there, but it's just a coincidence that this bunch of emission has lined up in such a way and it looks like a source, but it's actually just noise. And so this presents more challenges. And then another challenge is when you use lower signal to noise ratios, the signal pixels are on the same level as the background pixels, and there are more sources that pop up at this SNR ratio. But as you increase the SNR ratio, the signal is much more strong compared to the background, and so fewer sources pop up that are more obvious and more removed from the noise. So you generally get better results through using a higher SNR when you're doing source finding. And there have been many algorithms that have been developed to do source finding across all different wavelengths. But in this particular project, we are focusing only on radio wavelengths. And one method that we are comparing our deep learning source finding tool against is one based on Gaussian fitting, which is the Python blob finder and blob detector and source finder. So this is the same tool that we used for the first project in the context of counting components, but now we use it in the source finding context to compare against our method. And then in the last couple of years, there have been another couple of source finding methods deep learning methods that have been developed in the same task of source finding. So there is CLARAN, which stands for Classifying Radio Sources with Artificial Neural Networks, which uses a faster region-based convolutional neural network to detect sources as well as identify components that belong to certain sources. And so it can look at an image and exactly identify what are independent sources and what are the components that belong to the sources. And this algorithm has actually been trained on the Radio Galaxy 2 data release 1 data set, but this paper came out after we published our work, so it's a later work compared to what we did. And so it's able to characterize galaxies according to the number of peaks and number of components with accuracies greater than 90%, and it's also quite fast. And then there's also Deep Source, which was developed earlier this year, which uses a deep learning algorithm with some extra parameters that can only find point sources in the simulated images, and they also compare their results against PyDSF. Whereas in our approach, we use what is, I think, the first application of an autoencoder or a convolutional autoencoder to the task of source finding, and applying it to simulated images from the SKA data challenge across different types of sources of steep spectrum, flat spectrum, AGN, and star-forming galaxies. And so we have simulated data across three different frequencies, although actually we use two frequencies and 3 exposure times. And we've also injected sources at 3 different SNR ratios of 1, 2, and 5. And although the original images were 32,000 by 32,000 pixels, there's only a 4,000 by 4,000 pixel area which we know, which we are told where the sources are. So we have like a solution map for only a small area of this image. And so, yeah, we have our real data and we have our solution data that says where the sources are. And then based on this information, we've created 50 by 50 pixel maps like we've segmented the big map into these 50 by 50 pixel maps, and we've moved the maps along by 50 pixels each. And so we made sure that the entire area was covered. And we thought that, we think the deep learning approach will perform well in the source finding context when we set up the problem like this, because you can exploit the use of image augmentation to generate as much data as you need. But also you can move your blocks along by smaller pixels to get more information out of it and to get more images, essentially. And so this is a visual representation of what our real data looks like. So the real map is on the left with the 50 by 50 segmented pixels, and the solution map is on the right with the corresponding injection of solutions at a particular SNR. So we had data like this for the SNRs of 1, 2, and 5. And then what the data actually looks like when we feed it into our autoencoder is that, so you put in the real image at a certain frequency and exposure time in SNR, and you have the corresponding solution at a particular SNR, and so this solution data actually is like the label of the data. So we essentially want to replicate this solution map. And I'm showing here also some features that are detected by some of the convolutional layers. And we can see that AutoSource tends to output the solutions spread over several pixels rather than just one. I mean, sometimes it does localize them to one, other times it doesn't, but in the end, it's kind of the way it's giving out data is that it's giving a probability for the source to be in a particular area. So in a way, it's more flexible than other source finding techniques. And so the parameters that we've used, I mean, we have built our autoencoder using the Keras library, like in our second project. So we used just over 5,000 images for training and just over 1,200 for validation and testing. We used early stopping, so if the validation loss didn't improve for 5 consecutive epochs, we would stop training. We found it was necessary only to use quite a low number of filters and filter size in the different layers. And we used a dropout layer in order to minimize the effects of overfitting. And in order to ensure maximum information extraction, we moved the filters along by 1 pixel and used a batch size of 128 and the added delta optimizer. And so this is the results that we see at a signal to noise ratio of 1. So the different bars, the different colored bars represent the different runs of AutoSource, where the blue bar is AutoSource when you don't augment any sources. The orange bar is when you augment the sources that are steep and flat spectrum sources, and the green bar is when you augment all sources. And the red bar is PyBDSF. And so we can see that generally PyBDSF seems to perform better across this SNR, with the exception of the B1 data, so the 560 megahertz data set across star-forming galaxies and all sources. But most of the sources in the all source category are star-forming galaxies, so that's why they look similar, because there aren't as many flat spectrum, and steep spectrum sources in the all galaxies combined category. And we actually, when we actually randomize our source locations relative to the real data in order to quantify the effect of chance matches, we actually see that the additional benefit found by AutoSource seems to be due to random matches, at least for this SNR. So overall, PyBDSF does perform better at this signal-to-noise ratio, but it must be remembered that this is the worst-case scenario for chance matches, because this is the data set that's most populated with sources. At the higher SNRs, there's much less likelihood of chance matches happening, because there are fewer solutions available. And then to see visually what is happening for a couple of sources at this signal-to-noise ratio, on the left, I'm showing a real image and the corresponding solutions at an SNR of 1. And the third row shows the corresponding source location reconstructions, and it shows that it seems to recover the obvious source here, as well as this one here and this one here as well. But it seems to be confused about sources in the center, where it seems like it's missing some sources and maybe giving some false positives. And whereas PyBDSF just seems to to discover the obvious sources. And then in the second example, so here are the solutions for this example. We see that AutoSource recovers, again, the more obvious ones. It gives a false positive there, and maybe other ones here. And PyBDSF just discovers the obvious one. And then at a signal-to-noise ratio of 2, we see now that the AutoSource performance across the star-forming galaxies and all sources seems to be improved even more. And now it includes the B2, the second frequency at 8 hours, so the highest exposure, the shortest exposure time, so the noisiest data set at this frequency. So it seems to do better across the star-forming galaxies for this SNR, but PyBDSF seems to be performing better across the steep spectrum and flat spectrum sources. And we think that the reason why PyBDSF is better at recovering these sources is because maybe this SNR is still too low for AutoSource to pick up on the extended emission accurately. Perhaps it needs a higher SNR. And this is exactly what happens when we try the highest signal-to-noise ratio of 5. We now see that AutoSource is better on average at picking up on the more extended sources, so the steep spectrum and flat spectrum sources, compared to PyBDSF. So it can detect the extended emission more successfully at a high SNR, whereas now PyBDSF seems to be a little bit better at performing at detecting the star-forming galaxies and all sources, which are mainly star-forming galaxies. And so here's another example at an SNR of 5. So again, the real images and the corresponding solutions. We can see AutoSource detects this source, however, it gives some false positives. And PyBDSF fails to detect anything. And then in this image, here's the solution. AutoSource discovers it as well as gives a false positive. And again, PyBDSF doesn't discover anything. And so due to the fact that we use a reconstruction threshold in AutoSource, so what happens is we use a reconstruction threshold where we display pixels above a certain threshold between 0.1 and 1. And so as we increase the threshold, it reaches a maximum in terms of the F1 score, which is the precision recall optimized, and then it falls away again. We pull out the values at this place where the F1 score is maximized. And because we use this reconstruction threshold, AutoSource tends to output sources that are spread over several pixels that have a range of values. And so, yeah, this gives it some flexibility for giving the probability that you find a source in a particular place, rather than in PyBDSF or other source finders where they just say there's no source here or there is a source here. It's kind of black and white. We kind of like the flexible approach that AutoSource seems to give. And although, AutoSource detects more true positives and therefore misses fewer sources compared to the PyBDSF, which is the Gaussian feeding method. However, as a result, it also detects more false positives. So that's a drawback of our method. And the trend is that at lower signal-to-noise ratios, PyBDSF seems to extract the more extended type sources better. So the steep spectrum and flat spectrum sources, it doesn't need such a high signal-to-noise ratio to perform better than to perform better than AutoSource. Whereas the opposite effect is seen at higher SNR of 5, where now AutoSource is better at recovering these AGN type sources compared to PyBDSF. And so we have seen over our 3 projects that machine learning techniques have been very useful in our applications, and due to the avalanche of data that will be generated by telescopes, as they are detecting high quality sources at increasing sensitivity and resolution, using machine learning will become increasingly important. And we found in our projects that it's possible to classify sources based on how many components they have, and also the Fanarov-Riley class, and with high performance metrics. And we have also compared the performance of traditional convolutional networks against the recently developed capsule networks, which are designed to address some of the difficulties that are experienced by convolutional networks. But ironically, we found that at least for the data set the type of data that we had and the number of images that we had, the capsule networks seems to perform worse. But again, given more training images, maybe they will be performing better in the end. And in our third and final project, we have shown what I think is the first example of using an autoencoder in the context of source finding. And I think this is a novel application that deserves to be researched further, because source finding hasn't been looked at in this way, and we think machine learning techniques should perform good methods to perform source finding in the future. Yeah, thanks very much.
I'm curious about the source finder stuff. So source finding a radio images is something we've been trying to do on and off for 10 or 15 years in the context of like transients and stuff. So when you were comparing your technique, what was it called again? Autosource.
Yeah.
Autosource against PyBDSF. I noticed, and I think you mentioned this, but just to get it a bit more clearly, in the PyBDSF images, I saw no false positives, right? And yet in your images there were a number of false positives each time. But of course you can tune the threshold on PyBDSF. I could turn the threshold, the significance threshold down such that I was getting false positives. So why is it that you chose thresholds such that yours was producing false positives and PyBDSF was not? Is that because for each of those two, that's the optimum threshold for recovering the sources?
Well, we just chose the default setup in PyBDSF. We just wanted to see how like the basic setup would work, and yeah, we didn't really perform any more tuning of how PyBDSF performed. We just wanted like the vanilla performance, just to compare it.
You could adjust the threshold.
Yeah.
So you could have tuned the threshold down so that it was finding things that were more similar to what you were finding, I suspect.
Oh yeah, I guess we could have, but yeah, that's not something that we looked at. But yeah, in comparison, at least with the default parameters, yeah, it does seem like our method is finding more false positives, but it's also finding more true positives. So PyBDSF is missing some sources. So maybe if we change them, it might kind of PyBDSF might find more false positives, but then
I suspect if you tune down the threshold in PyBDSF, it would move towards the results you're getting. Because let's say you're finding 4 sigma things and PyBDSF only is finding 8 sigma things. It's not going to find false positives, but it's also not going to find 4 sigma real things. So I think that might be part of the difference.
Yeah. It's worth exploring other parameter spaces for both, definitely. Yeah.
So in your first test, you mentioned that you assumed that each square only had one galaxy in. And one of the things that we often can't tell the difference between is like true point sources and an FR2. So I wondered if you thought about removing that assumption and see what it was made.
For the 2-component extended class, well, yeah, I guess I mean, in the first project we just counted the number of components. We didn't assume it was an FR2. We just essentially wanted to see how well it would.
You assume that one of those components work on the same.
Yes. But yeah, I hadn't actually thought whether that would automatically assume that it's an FR2. But I guess you would look at then the pattern of the emission, like whether they're kind of angled towards each other, whether or not that might indicate that it's an FR2 if they're kind of pointing towards the same center. But yeah, we didn't make that assumption. We just counted the number of components. But what we did do is in the multiple component extended class, we did actually find that there especially looked to be some sources that were independent of each other, and so we actually visually inspected this data set. Like we went through like several thousands of them by eye and actually chose only like just under 600 that generally seem to be associated with the source in the center. So yeah, I didn't mention that actually at least for that class, for the multiple component extended one that had greater than or equal to 3 components, we did do some by eye tests. But for the other classes, we just ran with the assumption. I mean, I think it was fine for the compact and single component extended sources because, yeah, you just have one blob, essentially, where the compact ones are just spheres and the single component extended ones are a little bit more elongated. But, yeah, for the 2 component problem, yeah, I guess, yeah, we just said there were 2 components there, and we, I guess, assumed that it was one source. And then we didn't really think whether, how that would be interpreted in terms of being an FR2 or not. But, yeah.
So, again, on your first problem, all your images basically were very sparse because they were from Galactic Galaxy, which is based on first. Then you go into ASCAP and MeerKAT, that's low SVA. The images aren't sparse anymore. Every square you sort of cut out, you have upwards of 5 or 10 sources in it. It's that kind of scale. So, does that render the CNN obsolete because it can't deal with that level of complexity on a cut-out basis?
Well, I think they were, like, when they gave us the data, it was like a pretty small patch of sky where, it just seemed to be cutouts of individual sources, or at least that's what they told us the data was. But again, the more sources there are, the more chance there is that there'd be some components there that are not associated with each other. But I think for most of the sources, given that it was such a small patch of sky, that it was a reasonable assumption to make, at least.
LOFAR deacons, it's not going to be that situation. For each one of the squares you have to tell, as well as the FR2 or FR1, you'll have 5 or 10 fainter galaxies that are high signal stories, which is so much deeper.
Yeah. So I think for that data, you would just need to go from, like, you can't apply this trained neural network to that because it's targeted for this data set. I should mention that you probably need to go, either train a neural network from scratch, or you can try transfer learning where you get the optimized weights and biases and then you apply it and see how it does compared to one trained from scratch. But I think that there was a study that said when you apply a network that's trained on high resolution data, when you apply it to lower resolution data, it actually improves the performance compared to training it from scratch, but it results in a detrimental performance when you go the other way around. So if you train your neural network on lower resolution data and apply it to high resolution data, you get a worse result than if you trained it. Oh, yeah.
Just the shape of resources
you're
going to have. On the scale of an FR1 or an FR2 that you need to cut out around to get full morphology, you'll have 10 resources in that square.
Yeah.
So for the auto source, given that it seemed to, when I was looking at images, it seemed to perform like what I would find as a human person, right? Just when there was something you would find that the PyBDS would. And also the one question I had was, given that you have this issue with the spreading of the pixels in the output, could you maybe try representing the data in a different way so that the source image, right, is a very sparse thing. You just have maybe 1 to 10 points with her. I thought maybe using a sequence to represent that and then autoencoding it to a sequence could be a different way of doing this. Is there like a...
Yeah, I guess that could be. I mean, we didn't think of doing that, but I guess we could try that. But the fact that AutoSource gives the source location spread over several pixels, I think it's a double-edged sword. So, like, I think in some ways it's good because it gives a probability for finding finding a source in a particular place. But yeah, as a result, it gives more. It tends to detect more true positives, but at the same time more false positives as well. So it's a kind of double-edged sword. But at least I think it's more flexible than just the black and white approach of saying no, there's no source here, or yes, there is one here. So, but yeah, the sequence representing the pixels as a sequence, might be worth trying.
So one problem with CompNets is that they've got very bad precision and recall on with 3 or more components. So while CapsNets had worse performance on average, do you know if they had better performance in just that case, or something had 3 or more components?
Whether the capsule network performed worse, or whether it suffered more on the. From what I could remember, it was it was performing around the. I think it was performing the worst on the FR2s, so the ones with the most components on average. But I need to see the data. I just need to remember what it looks like. But I think it was, recovering the unresolved ones the best, but still probably a little bit worse than the Conv nets. And then, the FR ones were even poorer, and the FR2s were even poorer than that. So, it seems like, it aims to preserve the information in a certain area, but it seems like for the type of data that we had, maybe it was too far separated, or there's too much noise in between. The lobes are maybe a little bit too distant from each other, and it just hasn't had enough examples to learn properly. And we really changed so many parameters to try to make it work better, because I was convinced they should be better, but no matter what we did, it was just worse. Not drastically worse, but a bit worse than the Conv nets.
Ask the last question. So in the first 2 experiments, you relied on human input, and how accurate was that input? Was that statistically analyzed? How reliable it was?
Yeah, well, for the first project, the only part that had, I guess, more human input was in the 2-class problem, it was essentially no human input. Well, actually, I think when we looked at the multiple component extended class, we went through visually, so that was from us. But all the other classes were automatically assigned according to how many components PyBDSF found. But in the second project, it was inspected by expert astronomers by the LOFAR Galaxy Zoo. They clicked on the images, they found the components of maximum emission, and it was an automated algorithm that did the classifications, but it was cross-checked by someone, by third party, to make sure that the classifications were given by the automated. So in the second project, that was the most that was the data set with the most human input, and the most common, the most confident classifications into unresolved FR1 and FR2. So it had that had the most human input.